This video looks at model selection. How do we pick the best from a set of candidate models for a particular data set? We're going to think about three different techniques for doing that. The classical F-test, information criteria such as Akaki's information criterion, and cross-validation. And we'll walk through implementations of these three ideas in MATLAB. So to illustrate the ideas, we're going to use a data set from containing various climate measurements. Specifically, it's the data published in this paper a few years ago now. And it's data that measures the ocean heat content around the world. So measurements come from these probes, which are placed around the world in the ocean, and they measure the temperature, local temperature, and measurements from a number of these probes around the world are combined to produce overall measurements of ocean heat content in any particular year. Now, researchers have been gathering data from these devices since the mid-1950s. And so the data we're going to look at contains an overall measurement of ocean heat content every year since 1955 up to recent times. I think actually the data set we're looking at goes up to 2017. And what the paper was trying to do was to look at the trends in that data over the last 60 or so years, and then project those trends into the future to make a prediction about how the ocean heat content would change over, in the next 10, 20, 50, 100 years. So it's, following climate change over reasonably long timescales. So this is what the data set looks like. So the first column here just shows the year in which measurements were made. And then the next four columns all contain slightly different measurements of ocean heat content. You'll see that there are not a numbers in two of those columns because they're incomplete. They don't have measurements for various periods of years. Whereas the middle two columns do have complete data from 1955 all the way up to, down to the end, 2017. So we're just going to focus on one of these. I'm slightly arbitrarily going to pick the column number 3 here, and we'll use that as our data set. So I've taken the liberty already of preloading that data into MATLAB. Here we are. So just to very briefly talk you through what I've done. So I've just opened this exact text file that I'm showing here, scanned it in so that these 5 columns end up in this matrix OHC here. And we're going to construct some simple models of this data that will demonstrate the various model selection techniques that I want to talk about. Before we get going on doing the actual modeling, I'm just going to pull out the precise data set that we want to look at, specifically this column number 3 here. And we're going to focus for fitting models on most of these data points, but we're going to leave out the last 5 lines from 2013 to 2017 because we'll use those to a bit later to see how well models fitted to the data from 1955 up to 2012 can predict future unseen measurements. So I'm just going to use for now the data up to 2012 and leave out these last 5 measurements. So there are 63 years worth of data here. So I'm going to start by just defining number of time points is 58, so 63 minus those last 5. And then I'm going to construct a variable years, which is so from my matrix OHC, which is what's in this text file here, I'm just going to extract the first 58 of these values for the year. So these are the independent variables in our problem. They're known values, the years in which each of the measurements was obtained. So just put that into this variable years. So first 58 measurements from column 1. And then I'm going to extract my ocean heat content measurements just from the same set of entries in the third column there. So those are the measurements that I'm going to use. And I'm going to model them as a function of year. Okay, so, oops. Typo there. So let's have a look at this data. I'm just going to scatter the years against the actual measurements. Let's do it in black and give them a nice thick line width so we can see them easily. Make them reasonably large. Okay, that should do it. So here are our data points then, going from 1955 up to 2012. So you can see this sort of gradual increasing trend in the ocean heat content. And let me just tidy up this plot a little bit, move it over here for a second. So let's give it some labels and things, and make the font a little bit bigger. So you can all read it nicely. And so X label, so on the X axis, we've got the year. And on the Y axis, the ocean heat content. Okay, so that will do us as an initial picture. So then I'm also going to extract those last 5 years worth of data. I'll call them later years. So they're going to be later than the data that we use for fitting the models. So it'll be our number of time points plus 1 up to the end of that array. So the first column then is just the years. And I'll call them later OHCs. The same thing. In the third column. And let's just add these later OHCs to our scatter plot, but I'll do them in a different line width so that we can keep in mind the ones that we're actually fitting to and the ones that we'll use effectively as test data. So there, I've added these last 5 measurements at the top here, sort of not bolded, so that we can distinguish the training data effectively, these heavy set circles, and what is test data, these last 5 here. Okay, and I'm just going to define K to be our number of measurements that we're fitting models to, so that'll be the length of that OHCs array, and KL, the length of the later set of measurements, just to make our MATLAB variables consistent with the slide notation. Okay, so I'm going to define 4 simple polynomial models that we're going to start with to fit this data to. So we're going to have model 0, which is just a simple constant model. So the assumption in this model, I'm just going to call it a 0. So this model says then that the ocean heat content does not vary over that period of time. All those fluctuations just come from natural variation in the data. Climate change deniers model. Then, so that's our simplest model. And then M1 will be a linear model over time. Model 2, a quadratic model. model 3, a cubic model. So that should be y squared there, squared plus 3y cubed. Okay, so simple series of quadratic models. I'm just going to write down here parameter counts for each of these models because we'll need them later. So model number 0 has a parameter count n0 of 1. It's got one free parameter, a0. Model number 1 is 2, a0 and a1. N2 is 3, and N3 is 4. Okay, each of these models, of course, is linear in the unknown parameters, the a's here. So we can use linear least squares estimation to estimate those different parameters. In other words, we're going to solve the matrix equation A, that's our list of measurements, equals G, some design matrix, times our list of unknown parameters, X. And so our list of our list of measurements then is simply the OHCs. So that's the vector that I've called OHCs in MATLAB, OHC1, OHC2, down to OHC big K. And the sets of unknown parameters then are, so x0 is just the coefficient a0, x1 is a1, a0, x2, a2, a1, a0, and x3 is a3, a2, and a0. So to solve this matrix equation, then we simply need to define the design matrix G for each of these different problems. And it's fairly straightforward to see that for model number 0, G0 is equal simply to a column of ones. G1 is equal to, so the coefficient of A1 in model 1 is just the number of, is the years variable, Y. So I can write my design matrix for model 1 as the list of years 1 down to years K, followed by, actually I'm going to write it as a copy of G0, the matrix G0, which is just ones, of course, in this case. And similarly, I can write G2 then in terms of G1, where we've just got the years squared. I'm just going to abbreviate it to Y now. Y1 squared down to Y K squared, followed by a copy of the matrix G1, which, so in full it will be years, column of years squared, column of years, column of ones. And similarly, G3 is then years cubed followed by a copy of G2. Okay, so that defines our set of models then that we're going to use in the first instance on this data set. So let's just write that in MATLAB and we'll solve for the unknown parameters for each of these models. So let me start by writing G0 over here. So G0 then is just a column of ones of length K. Like so. Then our design matrix G1 is equal to years. I need to do some transposing here to get it in the right format for MATLAB to make a matrix out of it, but it's a column of the years appended to our design matrix G0. That gives it the right structure. And similarly, I can write G2 as a column of years squareds appended to our design matrix G1. So, and finally G3, we append this column of years cubed to the existing G2. Let's just have a quick look at those to sanity check. Just show the first 5 rows of G0 should just be ones. G1 should have the years in the, oops, first 5 rows, there we go. So it should have the years in the first column and then just ones. This is all timed by 1,000, of course, so I've got 1955 and then 1. Similarly, G2 will have years squared, years and ones, and G3 similarly will have a 10 to the 9. Let's just write it out for completeness. We'll have something, the first column is 10 to the 9 because it's approximately 2,000 to the power of 3. Okay, so those are our design matrices. So straightforward enough then to solve for each of our lists of unknown parameter values. So to start with X0, then will be the matrix divide of G0 by our list of measurements OHCS. And the same for all the others. So we get a slight warning with the cubic model here, basically because it detects some potential ill-posedness in inverting this matrix, which has got quite a wide diversity of magnitudes in the different columns. This first column is of order 10 to the 9, whereas the last column is of order 10 to the 0. These are all ones. In fact, this is just a warning, so it does successfully do the inversion and solve. It's just warning me that this matrix is struggling to invert it a little bit. But let's have a look at what parameters we get back anyway. So for X0, of course, this is just the constant model, and that gives us the value of that constant, which it comes out as -66. If we look back to our figure here, you can see that is, so -66 is around here somewhere, and it's approximately an average value of all of those different measurements. So that kind of makes sense. X1, of course, will contain the parameters of a linear model, not so meaningful in their own right. And similarly, the other models will contain additional quadratic and cubic terms. So we can then, having fitted that model, we can predict back the signals that these models predict for each of those measurements. So for example, I can write S0 is equal then to just G0 times X0, and that will give me the measurement that this model predicts for each of these years. Of course, it's a constant, so it's just going to predict that actually the measurement should have been -66 every one of these years. But I can do the same for each of the models, and then in a minute I'll add them to our figure so we can see how each of these different models behaves. And finally, the cubic model. And so let's plot the 0th order model, the constant model. We'll do that one in red. So I'm just plotting the signals as a function of years. Give this a nice bit more line width as well so we can see it clearly. So there we go. So that adds, there is our constant model again for these for the data points that we use to fit it. And so yeah, it just has a constant value around about the average of all of these different measurements. Let's add the others. So let's put the linear model, do that in green. There it is. So that obviously, gives us a much closer fit to that data than the, at least by eye, than the constant model does. Let's see how the quadratic model compares. We'll do that in blue. There it is. There it is. So you can see that we get, probably capture a bit more of the trend of that data compared to the linear model, particularly at the beginning and the end. It looks a bit closer. And finally, the cubic model. There we go. So it actually looks almost identical to the quadratic model. It's completely gone over the top of it there. If we zoom the figure in a bit, I think you can just about see the bottom of the blue curve underneath the pink one, but the quadratic and the cubic models come out almost identical. We can work out sums of square differences for these different models just to see how well they match our original data set. So let's do that just to see. So for model 0 then, sum of square differences is sum of S0 minus ocean heat content, the actual measurements, all squared. And that gives us a value, okay, what's that? 447,000, okay. Let's compare it to what we get with the other models. So with the linear model, okay, so that's reduced to something like half of what we got for the constant model. So substantially lower errors. And then for the quadratic model, that reduces again, probably again by a factor of approximately 2. And if we look at the cubic model, so it reduces very slightly, but there's no dramatic reduction in errors going from the quadratic model to the cubic model. And so intuitively, we might think, well, generally the aim in model selection is to find the simplest model that adequately describes the data. So here, comparing these 0th, 1st, 2nd, and 3rd order polynomial models of this data, intuitively, I think we'd select the 1st order model, the linear model, over the constant model. It produces much lower errors and looks like it fits the data better. Similarly, I think we'd probably favor the quadratic model over the linear model, again, sort of halving the errors, and certainly appears to fit the data more closely. But going from the quadratic model to the cubic model seems to offer very little benefit. And so, generally the approach in model selection is only to increase the complexity model if it gives a substantial benefit in terms of fitting the data. So here we might intuitively think we don't need the 3rd order model, we'll stick with the simpler 2nd order model. Okay, but that's what this section is about, is this trying to find or using various techniques for identifying the best choice of those models from a set of candidates like that. Okay, so if I just go back to the PowerPoint. So the first technique that we're going to look at is the classical F-test. And so the F-test in general, it tests the null hypothesis that the variances of 2 samples are the same, i.e. those 2 samples are drawn from distributions with the same variance. And that's useful here in model selection because we can use that hypothesis, we can frame a similar hypothesis that if the distributions of residuals of 2 models have the same variance, then the two models explain or fit a data set equally well. And if one of those models is then more complex, there's no justification for using the additional parameters of that model, and we would select the simpler of those models instead. So the F-test for model selection only applies when we have what we refer to as nested models. And two models are nested if the more complex of those two models, M2 in this slide, has all of the parameters of the simpler of the two models, M1, plus a few additional ones. So it is a generalization of model M1 that simply adds to the existing list of parameters that model M1 already has. And then, so the idea is that we test the hypothesis that the residual error variance is the same from these two models. And only if we can reject that null hypothesis that those two variances are the same, can we justify choosing the more complex model M2. So there's a standard kind of recipe for applying this classical F-test, which is that we compute this F statistic here. We'll come back to what that, to the different elements of that in a second. And under this null hypothesis, as well as assuming that we have Gaussian noise, then this F statistic has an F distribution with these two degrees of freedom. What exactly does that mean? It means that if that null hypothesis is true and the variances of these two distributions are the same, or the models are equivalent, then if we were to repeatedly gather separate data sets, fit our models, and compute the residuals, the distribution and then compute this F statistic, it would follow this particular F distribution. Okay, so let's unpick some of the contents of this slide a little bit. So first of all, the F distribution itself. So the F distribution is actually a family of distributions defined by these two degrees of freedom parameters. It's a distribution that looks like this. So it is only in the positive part of the real line, and is kind of peaked and skewed towards the positive side. But as these two degrees of freedom vary, they control the position of the peak, how far away it is from the origin, as well as how peaked the distribution is around its maximum value. So it can take that kind of family of shape, that sort of family of shapes, which are, and those precise features are controlled by these two degrees of freedom parameters. Okay, and so for any particular F statistic, then so if under the null hypothesis we know that it should be distributed according to one of these F distributions, let's suppose this one here, under the null hypothesis, then we compute some F statistic. If we find that that F statistic lies somewhere in the action part of this distribution, in the region where it's got reasonably high probability density, then we cannot reject the null hypothesis because it's quite likely that we would have made that observation under the null hypothesis. If, however, we compute a value of that F statistic, which is way out here beyond the main support of that distribution, then it's highly unlikely that that value would have occurred by chance under the null hypothesis that the two distributions are the same. So it gives us the evidence to reject that null hypothesis and accept the more complex of the two models. Okay, I'm going to write out this equation on the slide onto the virtual whiteboard here, because we're going to use it in a minute to implement this test in MATLAB. And as I do it, I'll just talk through these various quantities that appear. Okay, so in the F-test then, we have to compute this F statistic here. So F is, so K is the number of measurements as we defined it in our MATLAB. N2, so N's are the number of parameters. 2 here refers to the more complex model. So N2 is the number of parameters of the more complex model, -1. And then we've got this operator var of M2, the more complex model, minus var M1, the simpler model. And var here is the variance of the model itself. So I'm going to define it further down here. Let's write it here. Var of M is, so it's 1 over k minus 1. It's the variance of the predicted measurements from the model at the same values of the independent variables at which the measurements were made. So, so M here is the value of the model given the maximum likelihood parameter estimates and evaluated at our independent variable positions, the k different positions corresponding to our k different measurements, minus M bar, which is the mean of the model. So I'll write that down too. M bar is 1 over k, just the mean of the model's predictions at each of those combinations of independent variables. Okay, so back to our F statistic then. So on the numerator, we've got the difference of these variances of the model, and then we divide that by the difference in the number of parameters between the two models, multiplied by this operator E bar of the more complex model. And E bar is simply the mean squared error of between the model and the measurements. Okay, so so under our null hypothesis, then this statistic F follows an F distribution with degrees of freedom N2 minus N1 and K minus N2 minus 1. Okay, so now we've written that down, I'm going to go back to MATLAB and we will run this test for the models that we have just fitted to our ocean data. So first thing to do then is I'm going to compute these means here so that I can compute the variances in the numerator of the F statistic. So M0 is mean of S0. So remember S0 contained the predictions of model 0 at each of our corresponding to each of the measurements that we have. So to get this this mean here, I just have to take their average. Same for model 1. Two, 3. Now I can compute these variances for each of our 4 models. So V0 would be then, so it's going to be sum of, sorry, I'm missing a square here in the variance one. There we go. Sum of S0 minus M0 squared, all divided by K minus 1. Let's repeat that for the other models. Okay, so that's got these. Now we've got these variances at the top. We still need to compute this this E bar here. So this was the mean squared difference. Now, of course, we've already computed the sum of square differences. So the mean squared difference is simply these sums of square differences divided by k, the number of measurements. So E0 is sum of square difference is 0 divided by k. And similarly for the others. Oops. Let's do that. E1 right. And E3. Then last thing I need is the numbers of parameters of each of the models. So model 0 has just got one parameter, model 1, 2, and so on. So I think now I'm in a position to start computing these F statistics. So let's start by just performing this test between models 0 and 1. So we'll compare our constant model with our linear model. So if I compute the F statistic, then F01, that is, so K minus the N2 here. So this is the number of parameters of the more complex model. We're comparing model 1 with model 0. So that here should be N1, the number of parameters of our more complex model, the linear one in this case. Minus 1 times difference in the variances of these two models. So that's more complex model variance minus less complex model variance, V1 minus V0. And then divided by difference in the numbers of parameters of our two models, more complex minus less complex, times E bar of our more complex model. So that would be E1. Okay, and that is our F statistic. Okay, so there it is. So it gives us a value of 806. Okay, and then we know that if the null hypothesis, under the null hypothesis, this statistic should follow this F distribution with these 2 degrees of parameters. Let's have a look at that, that F distribution. So I'm going to create a new figure here. And I'm going to plot it over a range from 1 up to, well, let's plot a range that includes this value of the statistic that we just computed. So I'll plot it from 1 up to 1000. So this is FPDF is a MATLAB function that encodes this F distribution. That's the first argument is the value at which we want to evaluate the F distribution. And then the next two are these degrees of freedom parameters. So the first one then is N1 minus N0. And the second one is K minus N1 minus 1. Okay, so let's plot that and see what it looks like. Okay, so here it is. And so you can see, you can just about see that it has it's very peaked around close to 0, this distribution, at least on this scale from 0 is 1 to 1000. Let me make it bigger and we can see it a bit more clearly. So you can see all of the kind of the support of this distribution really is relatively close to 0 on this scale. And by the time we get up to, I don't know, a value of about 10 or something, it's pretty much reduced to 0. And if you recall, of course, the value that we've got back is 806. So it's way up here in the wilderness, very long way away from the part of the distribution that is significantly above 0. And I think, that's immediately telling us that we've got a value which is highly unlikely given the null hypothesis, because if the null hypothesis were true, we would expect to have a value that lies in the, the action part of this distribution. Nevertheless, let's continue and evaluate a p-value associated with this test. And so the way that we would do that then is so we want to figure out the mass of that distribution that lies before the F statistic that we've computed. In fact, we want to compute 1 minus that. So going back to our F distribution here, we have a distribution like that. And suppose our F statistic is here. The p-value that we obtain on our null hypothesis is the integral of the distribution above that value of F. And so I can also write that of course is 1 minus the integral of the bit of the distribution that's lower than that value of F, and we're going to work it out that way. So the p-value for this particular test then is 1 minus F CDF. Now that's the cumulative distribution function, which is this integral evaluated at our F statistic F0, 1 for the F distribution with degrees of freedom N1 minus N0 and K minus N1 minus 1. Okay, and that gives us a value of 0. So the likelihood, that's giving us a p-value for this null hypothesis of 0, which strongly allows us to reject the null hypothesis and accept the more complex of our two models, the linear one over the constant one. Okay, let's repeat that for the next pair of models. So we'll compare now the linear model and the quadratic model and compute F statistic 1, 2. So that's then K minus N2 minus 1 times V2 minus V1 divided by N2 minus N1 times E2. And so this time, okay, so we're getting a lower value of the F statistic this time, which looks, closer to the action part of the distribution this time, but still probably quite a long way. Let's once again work out the p-value for this particular test, FCDF. So now we're looking at F12, N2 minus N1, and K minus N2 minus 1. Okay, this time it's not actually 0, but it's still a very, very low probability. So p-value now of 10 to the minus 9. So again, with high confidence, we can reject the null hypothesis and accept the more complex quadratic model over the less complex linear model. Last one then, let's repeat for comparing the cubic model to the quadratic model. So compute the F statistic F23. And this time, so we're getting an F statistic of 0.28. So that sounds like something that is much more in line with the distribution that comes from our null hypothesis. And when we compute the p-value this time, okay, so we get a p-value of 0.6. Telling us that we cannot really reject the null hypothesis in this case. So we accept, we cannot reject the null hypothesis, which means we would stick with our simpler model, model 2, rather than being able to justify use of the more complex model, the cubic model M3. Okay, so that's the, that's the way the simple F-test works for model selection. before we move on to the next technique, I just want to have a look at how well each of these models that we've looked at so far predict the future measurements that weren't used to estimate their parameters. Remember, we left out these 5 additional measurements here. Because one of the ideas behind selecting this sort of notion of selecting the simplest model that explains the data is that through that philosophy, we should get the best prediction of unseen measurements. So by not selecting a model that's too simple, if we select a model that's too simple, then we don't capture the trends in the data, and so and that means that we don't predict well. Whereas if we use a model that is too complex, we can pick up subtle variation that just arises from the particular noise instance in our data, and that can disrupt the estimate of unseen measurements. But by getting that balance right between simplicity and fit to the data, we should be able to get to predict unseen measurements most closely. That's the idea. But let's just see how well each of these models that we've tested predicts these future measurements. So, of course, I reserved that 5 in order to use the models that we've estimated parameters for to predict those measurements. I'm just going to construct some additional design matrices that use these remaining 5 independent variables, that was 2013 up to 2017 as years, and then use those design matrices to get to predict measurements exactly as I did to predict measurements for the data points that we actually fitted to. So GL0 then is just going to have, again, will be a single column of ones, but this time of length KL, the number of left out measurements. And much as before, we can define these different design matrices somewhat recursively. So for GL1, we want the column of years, independent variables, and then we just append that to the design matrix for model 0. Like so. And similarly, for model 2, we just append now later years squared. Last model append later years cubed. Okay, so there are our design matrices for these unseen measurements. So now let's predict what those measurements are for each of our models. Exactly the same formula as we did previously, but with the new design matrix. And now, so having computed those measurements, then I'm going to add them to our plot here so that we can see how well they approximate those measurements that weren't used in the fitting. So let's start with our constant model M0. It's in red, wasn't it? And I'll do the line width of 1 just to distinguish it from the predictions of the measurements that we fitted to. And so this should, the constant model should just predict the same constant value. So we should see this red line extended to underneath these unseen measurements to the right. And let's do the same for the others. So now I add the linear model in green. Model in blue. and the cubic model in pink. Okay, and I think we see, as we'd expect, that the quadratic and cubic models predict the unseen measurements better than the linear, which is better than the constant model. We did see a bit more separation now of the quadratic and cubic models. You can really see the blue and pink lines slightly separated there. Let's have a look at the sum of square differences, or the errors for these unseen measurements or test measurements. So if I compute the test error for model 0, that would be the predicted measurements against the actual measurements squared and summed. So what do we get for that? Something like 250,000. Then for model number 1, that reduces by an order of magnitude down to 20,000 or so. Model 2, I expect we will see that reduce fairly substantially still further. Again, another order of magnitude. We're down to now 2,000 for model number 2. And finally for model number 3, so actually we see that it's reduced still further, despite our aim that by picking the simplest model that explains the data, that should give us the most robust estimates of future measurements. Actually here, the more complex one does predict them slightly more closely, although I think it's kind of fair to say that in this particular example, the difference between these two errors is well down in the noise level for these particular data. Okay, so let me go back to the PowerPoint here, and we're going to look at the next technique, which is so the next class of technique that we'll think about are called information criteria, and we're going to focus on one particular one, which is called Akaki's information criterion. And the way all of these techniques work is that we evaluate some information criterion, often quite a simple expression like this, for each of our set of candidate models. And those information criteria balance complexity with goodness of fit. And the idea is that, at least in the simplest mode of usage of these information criteria, we choose the model that minimizes this information criterion. And if we look at this simple expression, so this is the general expression for the Akaki's information criterion, it very directly encodes this notion of trading off between complexity and goodness of fit. So it simply increases linearly with the number of parameters n here, and decreases linearly with the log likelihood, or the goodness of fit. The more complex the model is, the more this increases. The better the model fits the data, the more this decreases. And so it's exactly that trade-off. And it almost looks as if that was just plucked in the air as a simple combination of those two concepts. But interestingly, if you look up the derivation of the information criterion either in the original paper or in this probably a bit more accessible book by Burnham and Anderson, you'll see that actually it comes from some quite basic, broad arguments, and from those broad arguments, you can derive this really quite nice, simple expression. Possibly a more familiar expression is this one here. This is a specialization of this general expression for the AIC here, which is specific for the case where we can assume independent, identically distributed Gaussian noise. And under those circumstances, then we get this more specific formula for the Akaki's information criterion. I'm not going to derive that, but I am just going to copy it here onto my virtual whiteboard so that we can use it in a minute when we implement the AIC. So I'm going to write then the AIC is 2 times the number of parameters plus k, the number of measurements, times log of the mean square difference, essentially, is what is inside this log. So I'm going to write that k minus 1. I'm going to write it slightly differently to what's on the slide there, just for consistency with my earlier notation. I'll write ak, the measurement, minus, we were using m of the model at the best fit parameter values evaluated at the Wyeth combination of independent variables squared. K is 1 to k. And one interesting point at the end here, in the derivation of this expression for Gaussian, for the AIC under the assumption of independent identically distributed Gaussian noise, there's the derivation uses an estimate of the standard deviation of the noise. And so effectively, the whole process estimates one more parameter than is contained in the model itself. And that has to be accounted for when in the evaluation of n that goes into this expression. So n must include 1 for the estimate of the noise standard deviation that goes into this derivation. So n must be 1 bigger than the number of actual model parameters. Okay, so let's implement this simple idea then for our set of models that we've been considering. I'll go back to MATLAB. Very straightforward, just kind of encode this formula. Let's bring that forward. So the AIC for the 0th model then is simply 2 times n0 plus 1 for this extra parameter that we need to count for estimating the standard deviation, plus k times log. Then, of course, we've already estimated this mean square difference. We called it E0 up here, didn't we? E0 is the sum of square differences divided by k, or the mean square difference. So I'm just going to use exactly that, log E0. And if we evaluate that, okay, so we get some number 523. And let's do the same then for the other models, for E1. $366, okay, so we're getting a substantially lower AIC for the linear model compared to the constant model, as we might hope. And for our quadratic model, 329.5, okay. And finally, for the cubic model, we get slightly higher value now than of 331, and that's because the errors are almost the same for these two models, but of course the cubic model has one additional parameter, and that pushes its AIC up a little bit. So, again, like the F-test, this procedure ends up selecting the quadratic model and suggesting that we can't justify the additional complexity of the cubic model. One advantage of the AIC and information criteria in general over the F-test is you'll notice that I haven't made any mention of models needing to be nested. And although we've been comparing a set of nested models up to now, we don't have that limitation with the information criteria. So we can happily compare models that have different structure and don't have parameters in common or generalizations of each other. And just to demonstrate that, let's consider one additional model here. Let's write model M4 of y is, so let's say it's an exponential model, b of x, a y plus c. And we'll estimate the parameters of this model too, and compare it to the polynomial models that we've been thinking about so far. Clearly, this is a nonlinear model. And so really to fit this model to our data, I ought to wheel out the heavy artillery of nonlinear parameter estimation. I'm not going to do that. I'm going to cheat slightly and find a way to linearize this model. And so first of all, if I just rearrange it slightly, I can write m4 of y minus c equals b e to the ay. And then if I take logs of both sides, I can write it like so. If I knew the value of c, I could then, oops, missed a b here. If I knew the value of c, I think I could then write this as the same kind of matrix equation that we used for our polynomial models above. I could write the set of measurements, now kind of pseudo measurements, as log of, what did I call it before? Log of OHC 1 minus C, log of OHC 2 minus C, all the way down to log OHCK minus C. So that could be my list of sort of pseudo measurements. They're not raw measurements, obviously, because they're shifted and log transformed. But then I could write that as equal to G of X, have a set of unknown parameters A and log B, for which my design matrix would then be something quite familiar, simply the list of years at which measurements were made, Y1 up to YK, and a column of ones. In fact, exactly the same matrix, if we scroll back up here, that we used for our linear model G1 earlier on. Of course, this all relies on having knowledge of this, this parameter C. However, in order to use this machinery here, I'm just going to make a guess at C. And it's actually not difficult to make a rough guess at what C might be, because if you think about it, C must be the asymptote that this exponential model tends to as y tends to minus infinity. So going back to our figure here, as we move along this year axis to a long way back to the left, C is the asymptote that an exponential model of this data would tend to as we go a long way back in history. And if you sort of think about an exponential model fitting this data, I think you can imagine that, you know, that asymptote is going to lie somewhere between minus 200 and minus 300. So I'm just going to arbitrarily pick a value in the middle there, and I'm going to call it minus 250. So just for the sake of demonstration, let's assume that C has a value of minus 250, and then that allows us to fit this model using this simple linear least squares estimation. Okay, so then I'll write C is, small c is minus 250. And then I can write my list of pseudo measurements. A is log of OHCs minus C. My design matrix G here, so I'm going to call it G4, of course, as we noted, is actually identical to the design matrix for G1. So I'm just going to copy G1 into there. And then we can solve for our unknown parameters A and log B in the usual way by matrix dividing our design matrix G4 by our pseudo measurements A. Having done that, so I've estimated the parameters. Now I can predict back what those, what the model thinks that each of the measurements should have been, S4. I have to work slightly harder here now. So I can, of course, type G4 times X4, now that we've estimated X4, but that's not going to give me the predicted measurements directly. It's going to give me log of the predicted measurements minus C. So I think I have to first take the exponent of that and then add this constant C to get to our predicted measurements S4. So doing that then, that gives me our predicted measurements. Let's add them to our plot. Here is our plot. And so I can now add what color should we use now? I'll use cyan for this exponential model, S4. And there we go. So we get a new set of predicted measurements now from this exponential model. So it looks not dissimilar to our quadratic and cubic models here, but has slightly more extreme variation, sort of increasing more rapidly towards the end here. I can, of course, also compute sum of square differences for this new model. Copy one of the older lines, adapt it, and we get, so what's that, one, and I think we'll find actually that's quite similar to the sum of square differences we got for model S3. In fact, it's almost identical, and they're not identical actually if we look at them. If I actually subtract one from the other, SSD3 minus SSD4, so it's not zero, but they're very similar to each other. So in fact, the sum of square differences of this new model are very slightly lower than they are for the cubic model, but not by very much. Then I can also define the number of parameters for this model. So of course we estimated 2 unknown parameters via our linear least squares, but then there was this additional C parameter as well. So I think there are actually 3 in total. So we'll say N4 is 3, and I can also compute. So E4 was that's the mean square error. So that's SSD4 divided by K. So now we're in a position to compute the AIC for this new model. AIC4 is then 2 times N4 K times log E4. And we see that that comes out now lower than either the AIC for the quadratic model that came out as 329.5, so only very slightly lower, and of course lower than the cubic model. So overall, then the AIC would select this new exponential model from this set of models. Let's, for completeness, compute the estimates for the unseen data points, these 5 up here from this new model. I can do that in exactly the same way as I've done previously, but now of course I have to take exponent of, so it's going to be GL1, the design matrix as before will be exactly the same as for the linear model, but I'm multiplying by x4, taking the exponent and adding this constant C, and then I can add that to my plot until years L4. I did it cyan, didn't I? There we go. And so we see that this new exponential model probably slightly overestimates the unseen measurements, whereas the cubic and quadratic ones slightly underestimate. We can compute let's compute the test error for this as well. So test error 4 is then sum of later HCs minus SL4 squared. And so that comes out as 826. Well, as you remember, the test errors for models 2 and 3, quadratic and cubic models, were of order 2000. So actually, interestingly, we're getting quite a lot closer to the unseen measurements with this exponential model than we did with the quadratic and cubic models. Okay, so that's using the AIC then to pick one of a set of candidate models. Don't need to be nested this time. There's another advantage of the AIC over the F-test, which is the ability to perform multi-model inference by calculating relative likelihoods of each of the models. And that's often done through the method of Akaike weights. So if you remember with the F-test, it's really just a binary decision. Do we or do we not accept the more complex model over the simpler one? Whereas one of the strong usages of information criteria is that we can compute these relative likelihoods, and that gives us a way of combining information from multiple models to get kind of consensus inferences or predictions by combining information from multiple models. The Burnham and Anderson book are a strong proponent of this kind of approach. And it really can, in situations where you've got a set of candidate models, you're not sure which one describes the data the best, it can provide a very nice way of including influences from lots of different models where there's uncertainty over which one is correct. And the way that's done then is to compute these Akaike weights for each of that set of candidate models. Very simple formula. We simply take the exponent of the difference of the AIC for each model with the minimum AIC divided by 2, and that gives us the Akaike weight. And that's then a kind of a coefficient in a linear combination of weightings when for computing some quantity derived from multiple models. We'll go back to our MATLAB window and show this in action to make it concrete. So if we go back here, then so to start with, then let's compute the minimum AIC over our set of models. So that's just the minimum of the array of our set of AICs. This should, of course, come out to the value for the AIC for model number 4, and indeed it does. And then from that, we can now compute the Akaike weight for each of our 5 different models. So for model number 0, that Akaike weight then will be exponent of the minimum AIC minus AIC for this particular model divided by 2. And we'll see that that comes out to a very, very small number, virtually 0, reflecting the fact that our belief in this model is low, so we're going to give it very low influence on a kind of a prediction that comes from the consensus over our set of models. We'll weight the ones that we've got more confidence in, given the AIC. So similarly then, let's compute the Akaike weights for the other models in exactly the same way. So we see also for model 1, we get a pretty low Akaike weight, 10 to the minus 9. But then for these models that give a better fit to the data, closer to the best one, we start to get some reasonably high values for those weightings. So, of course, model number 2 had the second highest AIC. Model number 3 was slightly lower, but still reasonably high, so it gets a reasonably strong influence. And model number 4, of course, was the highest one, so we should get an Akaike weight of 1 for that. So you can see the maximum one doesn't get that much higher in Akaike weight than the second and third highest. So now we've got those Akaike weights. The thing I'm going to infer is the value of these future measurements. So rather than making that prediction from just the individual models, I'm going to try and produce a consensus estimate of those future measurements, combining estimates from all 5 of our different models so far using these Akaike weights. So we'll write then our prediction of later year measurements from these weightings. It's just going to be a linear combination of the predictions from each individual model weighted by these Akaike weights. So well, a Keiki weight 0 times SL0 plus a Keiki weight 1 times SL1, and so on. Okay, just check that. So weighting of 1 times signals for 1, 0, 1, 2, 3, and 4. And these Keiki weights don't add up to 1, so we need to normalize by their sum. So that should give us our sort of consensus set of predicted measurements. So let's add these to our plot. SLW. I'll do it in black, but with a thick line width so that we can see it clearly. And so there we see, we get this, the consensus set of estimates for these measurements is actually quite nicely in between the exponential model that slightly overestimates and the quadratic and cubic models, which slightly underestimate and give us, something that actually looks quite good. Let's work out that test error just for completeness of the weighted sum. So that's then sum later OHCs SLW squared. Another bracket. And that comes out 400, whereas if you remember the test error for model number 4, the exponential one was 800, and for the cubic and quadratic, it was something like 2000. So, that consensus estimate from this multi-model inference, really does give us some substantial improvement in this case. Okay, so that is all I wanted to say about the information criteria. There are several others, of course. We've just focused on the Keiki information criterion here. Another famous one is the Bayesian information criterion. There are other things like minimum description length, minimum message length. All of them behave and sort of work in similar ways. Okay, so the last technique that I wanted to talk about is cross-validation for model selection. So this is kind of a more algorithmic approach to model selection, and really doesn't really think about this trade-off between complexity and goodness of fit at all, but really goes more directly for the intended outcome of model selection, of being able to predict unseen data more accurately. So there are lots of flavors of cross-validation. I'm not going to go through them all. I'm just going to focus on one, which is leave one out cross-validation, and how we can use that for model selection. Very simple procedure outlined in these bullet points here. So we simply take, for each data point in turn, we remove it from the full set of data that we're fitting the model to. So for the dark circles here, one by one, we'd remove one and fit our model to all of the remaining data points, and then estimate the error from that fit to the data point that we'd held out. Repeat that process for each one of these data points, and then take the average of those prediction errors and identify the model that minimizes that average prediction error. And that's the way the model selection is done. Okay, so as I say, lots of different flavors of cross-validation, which can be used in exactly the same way for model selection. There's a really nice description of the different types of cross-validation and what their different properties are when they're appropriate in this review paper by Arlott and Solis from 10 years ago or so now. Let's go back to MATLAB, and we'll implement this simple version of model selection by cross-validation using our suite of models again. So I'm going to start then by defining some accumulators for each of our models that are just going to store or accumulate as we go around this cross-validation loop, the errors for each of for each data point. We'll accumulate them as we go around a loop over the data points. So we need one for each of our models then. Now, for I, k is 1 to k. So for each of our data points, the first thing we're going to do is to construct our cross-validation data set. I'll call it CV, ocean heat contents. And that's our full set of data points that we fit the model to, the ones in bold here, minus the kth one. So I'm going to extract that in the following way, equals our full set of data indexed by this MATLAB operation setdiff 1:k, k. And what this is doing takes the difference between these two sets, the set of integers 1 up to big K and the singleton set, the integer little k. So the result of this is the integers 1 up to k minus without little k. So now I'm going to index our data set with that set of indices, which returns all of the OHCs without the little kth one. So that gives us our cross-validation set, just leaving the kth one out. Now, of course, if we just go back to our virtual whiteboard here, just flipping back to where we were thinking about fitting these linear models. So, of course, our list of measurements has now changed because we've removed the kth one. Correspondingly, to fit our models, we now need to remove the kth row of each of our design matrices. So that's the next thing I'm going to do. So I'll use exactly the same, this sort of setdiff function to do that in exactly the same way. So our cross-validation G0 is then G0 indexed by this setdiff thing again. So I want all rows apart from the kth one and all columns. Similarly, for the other design matrices. So I'm not actually going to bother with the model 4 here. I'm just going to stick with our polynomial models just to illustrate the idea of cross-validation for this. Keep it simple. So now that I've constructed those design matrices, now of course I can estimate the unknown parameters for each of our models in the usual way. Matrix divide our new design matrix by our new data set. Repeat for the other models. And now I need to, having fit them, each of those models, now our job is to estimate the data point that was missing. So I can now estimate the missing data point from model 0 just by taking the kth row of the original design matrix G0 and multiplying it by our newly estimated model 0 parameters. So there's that. And once again, repeat for the other models. And finally, so having estimated that missing measurement, I can compute the error with the actual measurement and add it to these accumulators that I defined before the loop started. So for CVE 0, I'm going to add the square difference between the kth data point, OHCSK, and the prediction that I've got from my 0th order model here. Squared. Repeat. And that should be the end. So let's run that. Okay, so we're getting our usual warning that the third order design matrix is a bit rank deficient, but it's just a warning, and it does the inversion anyway. It does that each time around the loop. So let's have a look at these errors that we've accumulated for our different models. And what we see then is that, so we get decreasing errors as we'd expect for our models of increasing complexity. So going from the constant model down to the linear model, we get a substantial drop in that prediction error of the missing data point. Halve the errors again going down to our quadratic model. And actually here we get a slightly reduced error score for our cubic model compared to the quadratic one. So actually, that tells us that cross-validation, unlike both the F-test and the information criterion, would have selected the third order model, despite the fact that the first and the second and third order models are really quite similar to each other. And that, of course, is kind of consistent with what I said about the cross-validation being focused on the ability of the model to predict unseen measurements. And we did, of course, see that the cubic model was slightly better at predicting the unseen 5 measurements than the quadratic ones. So that's somewhat consistent with the outcome here. Okay, I'm going to do one last thing before we end this video, which is going back to the purpose of this data in the first place. I was talking about the authors of this paper's intentions. Their idea was to fit models to this data and then extrapolate those into the future to make some statements about what we might expect from to see in ocean heating and general climate change in the more distant future, up to say the year 2100. So they didn't use any form of model selection. They simply picked a few different models and derived predictions from those, which they plot on this graph here. But let's see what happens from the machinery that we've developed in this video if we take probably the best model that we've constructed, this consensus one using the Akaki weights, and see what that tells us about projections of the ocean heat content into the future, into the year 2100. So we can construct again a set of simple design matrices just for this one single future data point of the year 2100. So for model 0, that design matrix will just contain a single one, like so. For model number 1, it's going to contain the year and the value 1. And similarly, for model 2, it will be 2100 squared, 2100 1. And for 3, we'll have the additional cubic term. So I can now compute estimates from each of our models using our fitted parameters. Let's see, so we want to include model 4 this time, of course, because I want the consensus from the Akaki weights. So for that, I have to take the exponent, use the design matrix for model 1, of course, and add this constant C. So let's have a look and see what each of those individual models gives us. So these are the set of estimates then from our different models of this future ocean heat content in the year 2100, very widely varying. As you can see, this is multiplied by 1,000. We get our sort of constant value from our constant model, which is the same as it is, the same as it was back in 1960 or something. Good luck with that. And then, of course, a higher estimate from our linear model, even higher ones from our quadratic and cubic models, because you see they kind of accelerate more rapidly than the linear one, and even the exponential model computing a fairly apocalyptic value of the ocean heat content that far ahead. And now, of course, I can compute our combined estimate from the Akaki weights. So I think I can adapt the expression that we had previously, this one here. So now, rather than combining the SLs, I want to combine SFs. The SFs that I've just computed. Done them all. 1, 2, 3, 4, 5. Yeah. So we'll call this SFW as well. And let's see what it tells us. So it gives us, sorry, yes, I did mean that. Okay, so it gives us this final value then of 3,000. And if we go back to the, just look at the graphs that came out in that, that were published in this paper, you can see that actually, from our consensus of models estimate of the ocean heat content in the year 21,000, we're actually at the very upper end of the predictions that these authors made. So slightly gloomy picture from our careful model selection and multi-model inference on the future ocean heat content. But on that happy note, I shall end this video.